A quick comment about the survival function. Take note, the complement of the CDF is your survival function, right? This is the notation that we use. This is your random variable X, and this is the value of X, okay? So because it's the complement of your CDF, we can write your survival function as equals to probability of X bigger than X, okay? Good. So we know this for a fact. When you take the derivative of your CDF, you will get your density function, your PDF. So we have your PDF will be the same as your negative of S prime X. What this means is we have, let's say we have, we know that Sx equals to 1 minus, right? So when you take the derivative, right? When you take the derivative, let's write it. Okay, when you take the derivative, what happens? We will get minus, right? Good. So now you can see that this thing here is the PDF. So that's how we can write this thing here. Okay, this relationship. Okay, good. Let's say we have in many exam questions, you will find they tell you that the PDF, okay, the PDF is proportional to some function, right? They'll tell you that again, we have a random variable and the PDF is proportional to some expression. So I've given you an example here, say it's proportional to 1 plus x raised to the power of minus 4 for values of x bigger than 0. What do you do in an exam, or if you see a question like this in a textbook, then you write your density function as c times this. Okay, so you'll have to find c though, because there's a good chance that you may have to find some probabilities, some expected values, and so on. So first you have to find c. How do you find c? All you need to do is, you know that your density function must integrate to 1, right? Your density function must integrate to 1. So use this idea and work out the value of c, because total probability is always equals to 1. Okay, quick example. We're given the density function is x over 2 for values of x between 0 and 2. It's 0 otherwise. Okay, 0 otherwise. If you don't see the word otherwise, sometimes it's written as elsewhere. Let me say it again, yeah? This density function only exists for values of x between 0 and 2. It is 0 elsewhere. That means it doesn't exist elsewhere, okay? Sometimes elsewhere is replaced with the word otherwise. And we have to find some expectation. What expectation is? The expected value of, we asked to find this, the expected value of the modulus of x minus mu. Oh, that's what we asked to find. So let's move the screen up a little bit. It's not a hard question, right? We know how to deal with modulus functions. So let's get through it, right? Okay. First off, we need this though. We need the expected value of x. That we don't have, right? So we can work it out, right? The expected value of x is what? Yep, x fx. Okay, and this is continuous. So we have to integrate from what? 0 to 2. That's what I've done here, x fx. Okay, do the integration yourself, and then you end up with the value 4 over 3. So basically what you want to find, coming back to the question, is this thing here. Okay, the expected value of modulus x minus 4 over 3. Okay, now very quickly, right? We have, if I have this thing here, this is equals to a when a is bigger than or equal to 0, and it is minus a when a is less than 0, right? That's the definition. Okay. Okay. So remember this, when we studied inequalities those days, if we wrote something like this, we will write it as x between a and minus a. Remember that? Right. That's the idea, right? So we have, I've written it here for you, right? Mod x minus 4 over 3 is x minus 4 over 3 when x is bigger than 4 over 3. It is minus, yeah, x minus 4 over 3 when x is less than 4 over 3. This thing here is the same as this thing here. Okay, so to find the expected value, just be a bit careful. Okay, just be a bit careful, because remember the values of x, right? The values of x are going from 0 to 2. So we have to be careful about 4 over 3, which is 1 1/3. So this part, just be a bit careful. I've done the expected value here. Expected value, right, or the expectation, if you like, is always xfx. The only thing is, it doesn't have to be x. It can be gx, right? So that's what we're using here. 4 over 3, okay? 4 over 3 minus x times your fx, which is x over 2 dx. Remember, this thing here is for values of x between 0 and 4 over 3. There you go. And for this portion here, between 4 over 3 and 2, which function are we using? Good. X minus 4 over 3. Don't forget to multiply by fx, and we have a dx here. The rest of it is just some integration, which is really easy to do, right? And plugging in some numbers. Be careful about this, right? When you plug in the numbers, use a calculator. Okay, that's okay. I've done it here for you. Okay, do the integration, plug in some numbers, and you will get the answer that they need. Okay, so keep in mind, okay, it's good for us to know this two relationships here for the discrete case and the continuous case. Yeah, discrete case and the continuous case. Okay, we have the expected value of x. There is a proof of this, right, in many of the statistics books, not a business statistics book, but a probability book. You'll find a proof of this. The expected value of x is the summation 0 to infinity, probability x bigger than x, right? That's for the discrete case. You have a summation. If it's continuous, of course, you have an integral going from 0 to infinity of the survival function, because this is the survival function, right? Survival function dx. So if you're given the survival function and we're only dealing with positive values of x, then you can find the expected value of x using these formulas, depending on whether they're discrete, whether it's discrete or continuous. Okay, it's good to know. Let's look at this. I've given you two expressions here. They're very important, really. So after a while, right, you'll get used to it, right? Conditional expected value. Conditional expected value. So we're talking about, let's deal with the discrete case first, yeah? The expected value of x given. That's what we mean by conditional, right? What is the expected value of x? Given that x lies between j and k inclusive. Remember this? Probability of A given B. What is it? Good. Probability, okay, over probability of B. So you have a denominator, which is a probability of this thing here, right? That condition. So you can see this straight away, yeah? This is your condition. You have a denominator here, which is a probability x is between j and k inclusive. The top part here is A intersection B, so which is an expectation, right? So I have xpx. I repeat, this xpx. Be careful. You're summing here. You're summing here because we are dealing with the discrete case, and you're summing from what? Good. From values of x going from j to k. That's it. Don't forget, this is xpx. Similarly, we have something for the continuous case, except that here the numerator will be the integral going from j to k, x fx dx, and the denominator is the same. The probability that x lies between j and k inclusive.